So welcome to our last of the officially scheduled didactic hands-on-ish things. This one builds nicely off of this morning's talk by Sebastian that takes some of the concepts of the linked data and semantic web and applies them to the real-world issues of neuroimaging data and analysis. We have with us for this segment David Keeter from UC Irvine, and I will turn the floor over to him.
Thank you. Thank you for inviting me to this training session. Again, my name is Dave Keeter. I'm from the University of California, Irvine, and have been working with the ReproNIM team for quite a while now. So, from Sebastian's talk earlier, you learned a little bit about semantic web and linked data. You've also, I'm sure, seen or heard of the FAIR principles many times at this point. This idea of making data, more findable, accessible, interoperable, and reusable. So what you'll see today is our attempt to sort of use the linked data models to capture metadata from neuroimaging studies and use those linked data representations to better find data, specific data that you're looking for across data sets, and to make data sets more interoperable by making sure they're properly annotated. And we'll focus, the first half of the talk on how one, annotates their BIDS data sets. I'm sure a lot of you are familiar with the brain imaging data structure in BIDS, probably use it. And so there are some things you can do to your BIDS data sets to make them more reusable and more interoperable with other projects. So we'll look at some of that and use OpenNeuro, the OpenNeuro database, which contains a lot of different BIDS data sets as an example. And so again, what we're trying to do here is really enable both extraction of specific cohorts across data sets, things that you might be interested in, findability of data, and attempting to, sort of enable large-scale analyses with some of the metadata that we capture from these data sets in conjunction with using DataLad, which you've learned a little bit about already. So we'll get started here and we'll start looking at a BIDS data set. So if you're unfamiliar with what a BIDS data set or the data structure looks like, on the left here, you have your regular, sort of DICOM directory that comes out of your scanner. As many of you know, who probably have been doing neuroimaging for a while, you have a bunch of DICOM files, and they're named with these funny sets of characters, these IDs. And, traditionally, I think every single lab that I ever worked with, we'd all write our own custom converter that would take information from the DICOM files and rename files and organize them on disk. So this was the slide I had before when I'm talking about FAIR data. It just has the definitions and so forth. Okay, so now we're on the BIDS data structure. So on the left-hand side, you can see the regular DICOM directory that or DICOM files you might get out of your scanner. The right side is this BIDS data structure. The idea being that it's an organizational structure to tell you where to find certain files and file types. There's metadata and interesting information here encoded in the directory structure, like you have these directories called ANAT, FUNC, DWI. Those directory names tell you something about the data that's contained within them, so that has meaning for us to extract during our metadata extraction. Also, the file names, as you know, have metadata in them, like the anatomical file name will say, the contrast type there on the end with this T1W string. So there's metadata in the file names, and then there are these additional files like this participants.tsv file, which can be there or might not be there, but if it's there, it generally contains some variables in it. Oftentimes, you'll have age, handedness, maybe gender. You may have additional selected variables from a whole myriad of assessments that you collected during the course of your study. You could also have another directory called Phenotype, and that subdirectory might contain the full assessments that you collected during your the course of your study, whereas the participants.tsv file usually just has like summary variables or selected variables. And so one of the problems with just a standard BIDS data set without any data dictionary, so in BIDS, you have this capability of adding they call it a sidecar file, this participants.json file. So for any TSV file, you can add this JSON sidecar file, which essentially is meant to contain a data dictionary. And so without a data dictionary file in your BIDS data set, then it's possible that your participants.tsv file, the data that's in there is, again, unclear or ambiguous as to what those variables are, how they're coded. You could have a column in the participants.tsv file with gender as a column name and the values of 0 and 1, but there's no mapping to is 0 male, is 0 female, is 0 other, who knows. So, having that JSON sidecar file is important, but also having the correct properties in this JSON sidecar file, like a real data dictionary, is also important. If for every TSV file in your BIDS data set, you have a JSON sidecar file, that's good. It's still hard to query across BIDS data sets using that setup, because each of us could call the same variable coded in a slightly different way by a different name. So, you might have a variable that says age in one data set, and that's meant to be like postnatal age in years. You might have a variable in another data set, scan age, and that may be in years as well, or months, but it might be the age at which the scan was acquired. And querying across these data sets for just, if you're just interested in finding data sets where there's a measure of age, and at the highest level, you just want to look across lots of different data sets, and you just want to know, do they have a measure of age? Because if they do, then later on, if they have these JSON sidecar files, I should be able to go in and interrogate those sidecar files and find out more about how one study coded age versus another study. And so, those are the sorts of things we're trying to facilitate with our semantic BIDS or repro BIDS. It's a JSON sidecar file. If that sidecar file contains the appropriate information, we can create these NIDM metadata files. These NIDM metadata files have both that information from the data dictionary plus metadata from this entire BIDS directory structure, along with information about the images. And so from there, we can start to query across data sets by asking for data sets with certain concepts in them, that measured something about age, that measured something about anxiety disorder, and so forth. So we're going to see how to do this with some of the PyNIDM tools. I'll talk a little bit about NIDM later, but right now we can just think in terms of BIDS. So we have these BIDS data structures. We could have secondary assessments that are either in the BIDS data structure or are separate from the BIDS data structure. We have some tools that will load in the BIDS directory structure and these TSV files. It will it'll allow you to annotate the data much like creating a data dictionary. If you're storing these things in REDCap, we have a way of parsing the REDCap data dictionary automatically, but let's just pretend like you don't have that. You'll iterate through each of the variables. You'll set up your data dictionary with the tool. You'll tell it, you'll answer questions about the data types and ranges and things like that. And then you'll be offered the opportunity to associate your variable, which we're calling your personal data element. It's a data element that you collected as part of your study. It's like personal to you. You might have coded it different than the lab next door. Well, we want to associate selected variables from your data set with broader concepts. So the idea of a concept association, again, is let me think about which variables that others might be interested in searching across data sets for. Like, these are high-level concepts. So yeah, of course, age and gender are important things, handedness, but also things like, anxiety disorder, a measure of anxiety disorder, a measure of memory, those sorts of things may be of interest to people when they're trying to identify cohorts to use for their study. Okay, so if you looked at the participant sidecar file in a BIDS data set, this is from the BIDS specification document. Essentially, it looks like this. It's a little JSON document, JSON document with the keys or your variable names. And then there's some of these properties that are specified in the BIDS standard. So we're going to try to help you make this by with the PyNIDM tools. So this slide is for the more practical experience. There's a list of things that you need to do to kind of get this to work for you. If you want to try it afterwards, you can pip install PyNIDM. You saw how to install DataLad. You can install DataLad. And then using DataLad, you can grab, really any of the BIDS data sets that are out there. But for this practical experience, I think we are focusing on the ADHD 200 study, the Brown site. So you can DataLad install that. To do the concept associations, you need to be able to search the interlex. The way the code does that is it uses an API key that's specific to your user account. So you'll have to do this little bit before you run the tool. Go to the scicrunch.org site, sign up for a free account if you don't have one. Go to your account settings and API keys and create yourself a free API key, and then set an environmental variable in your bash or terminal interlex API key with your API key, and then our tools will use it. You can still run our tools without it. You just won't be able to associate concepts, those higher level things that are very useful for querying across data sets. But for just to try it out, you don't really need that. Okay, so this is what the Brown BIDS data set will look like when you get it from DataLad. There'll be, the participants.tsv files, some other JSON files, a bunch of subject directories, and so forth. If you were to open the participants.tsv file, it would look like this. So you've got some columns that sort of make sense to you right away. You've got a gender column that just says male and female. That's pretty semantically clear. You have an age column. And if we assume that this site followed the BIDS standard, this should be, because the BIDS standard suggests that age is coded postnatally in years. That's what we're going to assume this column is. This particular data set does not have a participants.json file. In fact, none of these ADHD 200 site BIDS data sets do. So, but you'll see. So you'll see handedness, you'll go, okay, that's right and left. That kind of makes sense. Now I have these verbal IQ, performance IQ, and full IQ measures. Not entirely sure what those are, but we can make some assumptions. So if one were to go online and look around for the ADHD 200 data dictionary, they would find one. And this is what they would find. So it tells you that, there's two genders in their study. There were 3 handednesses, even though in the data set that I got from Brown University, I don't think there's anybody who's ambidextrous. So you wouldn't know that without having the data dictionary. And then there's a diagnosis. Well, we don't have any of those in the Brown site file, participants.tsv file. There's some IQ measures. It could be any of these, but we don't have that information. There's nothing here about age. That we do find in the data sets. There's really nothing here to tell us about what the difference is between verbal IQ, performance IQ, full IQ, and of course, which IQ measure was used for that specific measure. So without the JSON sidecar file, I think you can see that, first of all, we don't precisely know what each variable means in those data files. If we go to the data dictionaries, it's great that they have a data dictionary, but it's not sufficient, right? It doesn't tell us units, doesn't tell us what kind of IQ measure was used for what kind of, for the specific columns that are there. So we'd like to do better than that. And so some of the tools that we built are to help you do that. So if you were to run, so we have this tool in PyNIDM called BIDS MRI to NIDM, and you give it a little -D in the directory location of your BIDS data set. And you can add this flag called BIDS ignore that will, any files, it'll add an NIDM file to your BIDS data set, but it'll also add that to the .BIDS ignore, which tells the BIDS validator, ignore this file. And so your BIDS data set is still a valid BIDS, but it has this extra metadata file. And if you run BIDS to NIDM, essentially what it does is it opens up all those TSV files, and one at a time it goes through and it grabs the column header. So in this case, it's gender. And it asks you, because remember, this is specific to your use case, to your project. So this is up to you to define. So here you have an opportunity to describe your variable, to give it a label. You can choose the label that's in your participants.tsv file, or maybe you want to choose something a bit more semantically meaningful if you had a weird variable name, like a lot of assessments might have P1, P2, P3, P4 as the variable names, and you might want to put something more expressive. So here, what we're doing is we're continuing now. It asks you what kind of data type this variable is. It asks you if it's categorical. It asks you, how many categories are there. It gives you the opportunity to associate text strings with numbers, like if you're putting things into your database, oftentimes you'll put them in your database with numbers instead of the strings. And so after you annotate one such variable like this, so you've made a annotation of your personal data element, that's something that ends up in the participants.json file. And now it's asking you for an association with a concept. And this is, kind of, again, up to you. So you have to think, is this variable something that people would be interested in knowing about this data set if they were querying for cohorts across many publicly available data sets? So we don't want to get down into the weeds and say, I want to associate a concept with a measure of the person who QA'd this data set. Something like that is, probably not useful for people querying. Like, they're not going to query across data sets and say, I only want data sets where there's a QCer that was QCing this data. They might, but but for gender, of course, almost always you'll want to know for cohorts, okay, I need a measure of gender. Like, I need to know their gender, I need to know their age, that kind of thing. So you'll get an opportunity to associate a concept with this particular variable. The way this works now is it queries three things. It queries the InterLex information resource at UC San Diego, and they kind of slurp in terminologies from lots of places. It queries the Cognitive Atlas from Russ Poldrak's group, and it queries the NIDM terms. So the terms that are, so in NIDM, and I'll talk a little bit more about that later, but in NIDM, we try to, we're building a semantic web model for neuroimagers. So we try to amass terms that are specific to neuroimagers and put those into the NIDM terms of vocabulary, and where they don't exist, we'll define our own. So it searches NIDM terms as well. So in this case, what we're going to do is we pick the most generic definition of gender. And so in this case, we'll pick the one from NIDM terms, which I think is just a generic definition of gender. Now, if the way this concept query works is it uses your variable name and it tries to, or your label of your variable that you selected in the first part, and it tries to query the InterLex based on that label. So if you don't find a concept that you think makes sense, you can choose one of these selections is to change your query string. So you can change it. So if your variable name was P1 and it searched for concepts with P1, you say, well, it didn't find anything, but you know what P1 really is. Oh, it's age. So I'm going to change my query string. I search for age. I get back a whole bunch of concepts, and I look for the most generic ones. And the hope is that the best match, these are fuzzy matched. So the best scoring matches will be close to the top of each category. So the lowest numbers. And we're currently doing work to improve this so that the searches come back with the most meaningful or the best matches, and filter out the rest. So that's kind of how the annotation process works. Once you're done doing that, it will create a participants.json file in your bids directory. It looks like the one we saw from the bids standards documentation, but it has some extra information in it. And the extra information won't break bids, but we think is useful and necessary to make these data sets unambiguous. And so here you'll see like a couple of so you'll see the variable handedness here. It's keyed based on the variable name you used in your participants.tsv file. There's a bunch of these properties that we've collected with that annotation process that we just kind of saw with the animation. And then there's this is about extra property here that's not in the bids specification, but it's the link out to concepts. And so in here, we add the URL for the concept that you've attached to this variable, and we pull the label from that concept because it makes the, which you'll see a little query tools, better. So that's what these look like. You can have many concepts, more than just one concept associated with the variable. That's not a problem. There's also this NIDM file that was created in this bids directory, and we'll look at that in a moment. What you saw for the annotation process is a command line tool. So if you've ever played old school games like I think Zork or Legends of Zelda, it's very much like that. It asks you questions. We are building, or Sanu from MIT and Satra Ghosh's group as part of the NIDM terms. Grant is building a little JavaScript version of this annotation tool that will be available soon. And it does essentially the same thing as we just saw from the command line version. So that will be nice to have. Okay, so what can we do with these annotated bids data sets? So what we did was we ran the exact same, bids MRI to NIDM tool on the bids data sets that are available from OpenNeuro using DataLad. So we use DataLad get a data set from OpenNeuro. If there's a participant.json file there, then it was used. And if there wasn't one there, then we went through the variables and said, okay, do we think we know what these are? And if not, we go back and start to ask the data set providers for a little more details. And we started to associate the certain variables in those data sets with concepts. And so what you'll see here is a little binder demo, and there's, I think, links at the end of this presentation to these, that uses all those participant.json files for those OpenNeuro data sets and builds a little query tool with Python by loading those JSON documents, pulling out the is about concepts, the labels, and making a dropdown. And then allowing people to start to select amongst the annotations of the OpenNeuro data sets. So there's lots of interesting, I think, concepts here that people might be interested in when they're, say, hey, I want to find data sets in OpenNeuro. In this case, okay, we want to find a data set with some measure of anxiety disorder. I think the next thing it'll do is age. Of course, we need age. So we'll have a measure of anxiety disorder and a measure of age. We want data sets that have both those things. So this comes back with the result. There's 3 such data sets in OpenNeuro. And then I say to myself, wait a minute, of course, I need to know what their gender is or sex. So I'll run that query again, and I find out there's only 2 data sets. So this is the idea. You annotate your bids data sets. This kind of query tool we're hoping to have added to the OpenNeuro interface so that you can, query across bids data sets. Now, so all we've done here is really created data dictionaries, added some concept annotations, and stored them back in the bids directory structure. This query interface was built using those JSON files, nothing else. So we didn't use the NIDM files here. And why do we care about then having the NIDM files? Real quick, before I get to that, we could look also at the frequency of concepts used. So how often was a particular concept used to annotate an OpenNeuro data set? And it tells us some interesting things about the data sets in OpenNeuro. I think one of the most interesting things is that 70% of the data sets in OpenNeuro had a measure of age. Only 53% had a measure of sex, but 67% had a measure of impulsivity. So that's pretty funny, because you'd figure the first 2 things you'd put in your data set are age and sex, and then you would add some other things. But anyway, you can see, by annotating your bids data sets and linking concepts in, we can tell a lot about A, in this case, what's in the database itself. B, what kind of, and these are, neuroimaging related data sets, right? So, or I guess imaging related data sets in OpenNeuro. So what kind of concepts or kind of data are being collected along with imaging? So So now we have this NIDM file. So why, if we built this nice little query demo based on concepts, why do we need the NIDM file? Well, the NIDM file has a lot more rich information about the imaging measures, the imaging data contained within the BIDS data set in this nice linked data framework. The little query binder demo I built from the JSON files, I had to go in and mechanically, basically code up how we're going to do AND queries, how we're going to do OR queries in using the NIDM file, because it's based on the semantic web and linked data. We have a query language already written for us. Actually, there's a few, but Sparkle is the one that we use most often. So we have things to build off of, and we have richer metadata and richer information in those NIDM files than just the JSON sidecar file for, say, your participants.tsv. So we'll have a little look at that. I think you might have seen this, but the basic NIDM structure is there are projects, sessions, and acquisitions. Project contains sessions. Sessions have acquisitions. These acquisitions have an activity, the activity of acquiring this data, whatever it is. And then the entity, which is the object produced by that acquisition. So this, acquisition entity could be an assessment. If the acquisition activity was the activity of performing an assessment on a participant, or it could be the MRI data if it was the acquisition was collecting an MRI, and so forth. So just using these basic building blocks, you can create very complex graphs of the information that you've collected as part of your study. And so the thing on the left is essentially that same structure you just saw: project, session, acquisitions, repeated over and over again for a bunch of different participants. And on the right, we can use these same sort of structures the same sort of structures to annotate derived data, or in this case, it's Freesurfer brain volume computations, but one could think of really any other computation. So you could use these same sort of structures with activities and entities, and have links back to the original data that was used to compute these, in this case, brain volume. So now you're building in provenance with the original data, the experimental metadata on the left, and the results on the right, all together using the same sort of vocabulary backed by semantic web tools and techniques. So these graphs can be written to disk. So these are graphs. We're forming graphs of information. That's kind of what linked data is all about. Forming a web of linked data is essentially forming a graph of information. And so there's ways of writing this graph out or serializing it to a file on disk. These files, almost all of them, except for one that says binary RDF, are text-based. So these are files you can open up in your any text editor, and you can look at the data. Now it's a graph, so it's mentally hard to see that graph structure from just this text file, but the computer can read these text files very easily. I mean, it's a very structured text file, much like XML or something like that, if you've ever used it. So there are different ways of serializing it, and one way that we like a lot is called this terse RDF triple language. You saw that in Sebastian's presentation. It's called Turtle for short. Turtle is kind of, I think, easier for humans to read. These files aren't meant for humans to really look at, but we wanted to make them a little bit, easier for people to use by making them as readable as possible. And so the way you read them, you saw from Sebastian's presentation that there's a subject, a predicate, and an object in each statement. And so a turtle file is pretty easy to read. The first thing is the subject. So this is like some weird ID. The second thing is the predicate. The A is short for RDF type. They just replace it with A. And then the thing after it is the object. So this is saying this NeuroImaging thing is a NIDM project. Okay, well, NIDM project is a URL. I should be able to go out, understand what that means. It's saying this thing is an IDM project. Okay, this thing, DCT types title. Okay, well, if I went to DCT types, if I dereference that URL, I would find out that this was saying, here's the title of this project. and so forth. So you can read down through here and you can say this thing has a license, this thing has an identifier, this thing has an author, this thing has a creator, so forth. Okay, so you could also serialize this as JSON LD. That's another popular serialization method because a lot of people find JSON easy to use, both in Python code and in text editors, grep, those sorts of bash or command line tools. JSON's easy to use, but JSON in and of itself isn't sufficient because the keys don't mean anything without a data dictionary. So JSON LD is essentially a way of providing a data dictionary for your keys. That's these context files or context headers, and also lets you encode a full graph in a JSON document, which makes it a little bit more complicated than just a straight, flat JSON file. But it kind of mixes both the best of both worlds. Easy to use JSON. You can load it as a dictionary in Python, no problem. The context file to give information about the keys, and then some additional structure to allow the storage of graphs. Okay, so if we look at inside the NIDM file, and we're going to look at it in the turtle format, we'll look here at an acquisition object, one of those entities. So this is something, and without the graph structure, we don't know what this is connected to, but we know it's a acquisition entity. It stores some data about an acquisition. I know this is an MRI acquisition. Of course, you could tell that too if you started reading down through this metadata. So this metadata was pulled out of the Brown, I think this is the Brown, yeah, Brown data set from the bid structure, from the bids data structure, naming conventions, the way that the directories are named, in any JSON files that you might find in there beyond the participant sidecar file, which we already went through. So there are other JSON files in your bids data set. If you've converted the data from DICOM, then it has some rich metadata in those JSON files. But anyway, you can read down through this and you could say, okay, for this thing, it has an echo time, flip angle, so forth. It has some other parameters about the image acquisition. It tells you a little bit about the contrast type in this image and what the intended use was for this image by the dataset provider. So this says this is an anatomical scan. It was meant to be used as an anatomical scan. Doesn't have to be used as an anatomical scan, but it gives you some information about that. And because you had datalad installed, that pip datalad install command, PyNIDM Tools, when it creates this NIDM file, it tries to go out with datalad and tries to find if there is a location on the web where it can find this data file. And so this prov location predicate here, that it exists and it has this URL means that it found this particular file, this T1 weighted imaging file from this particular subject on Amazon S3. And we know that ADHD 200 makes their data available on Amazon S3, so that makes sense. But certainly super useful information to have if you want to create automated workflows that go and pull certain imaging files from, in this case, Amazon S3, and use them. You have the links there. What else is in this NIDM file? It encodes your data dictionary. That was the annotation thing we did before. It was in the participant.json file. It's also here in the NIDM file. And then it has the assessment. In this case was an assessment from the participant.tsv file that contained age, gender, handedness, IQ measures, and so forth. Then it gives you some metadata about where this stuff came from the participant.tsv file. If that participant.tsv file was available in the Amazon S3 bucket, it would have a link for that too. But if it doesn't, then it tells you the local location where it found this file when I ran the annotation step. And then it tells you something about the participants and their subject IDs and information about the project that it's pulled from the dataset description file. Okay, so once we have all that, what can we do with it? One thing we can do with it is we can use the PyNIDM tools to query. So there are a variety of ways to query NIDM files, and this is all work in progress. So we're constantly improving this. But basically, you can use this PyNIDM query tool, and you have a couple different options of how to do queries with that. Some more sophisticated than others. And what we're working on now, and there's some working examples of this, but I don't want to push it right now. You can use this thing called a Blaze Graph, which is a local graph-based database. It runs as a Docker container, and you can run the Blaze Graph locally with Docker run. You can load your NIDM files. There's a command in our READMEs that tell you how to do that, and then you could use Sparkle if you knew how to write Sparkle queries to query those data. We're adding Blaze Graph capabilities to our PyNIDM query tool, so you don't have to really think about much of this stuff. It will improve query speeds when you're starting to query across many NIDM files. So the basic PyNIDM query tool has a bunch of options for you. You can give it a list, a comma-separated list of NIDM files. So this doesn't have to be one file. It can be 10 different project files. The more you put in there and the bigger they are, the slower the query is, obviously. And so when these things get really big, like if you want to query across like 20 different projects, or one project has thousands of participants, that's where we need the Blaze Graph database to help improve the query speeds. But for your, for the single projects you have, you can use this, or, smaller data sets, you can use this. So you give it a list of NIDM files, you have some parameterized queries, and there are some READMEs associated with this that you can learn about, but there's some parameterized queries for you. And then there's, and then there's this, there's a REST-style query interface, which we'll see in the next slide. So here we'll do some queries of that brown dataset NIDM file. So I'm on the command line here. I have PyNIDM query. I give it just in this case, one NIDM file, but you could do a comma separated list. I'm just going to do this parameterized query -p. It tells me, the subject IDs of the individuals in that data set, along with their object identifier, which you don't really need. So another, let's see, so now we're going to use the REST API. So you can use the -u parameter, the REST API, and say, tell me what the project IDs are for all these NIDM files that are in the NL list. We only had one, so it gives one project ID. So then I can say, hey, let me look at that project ID and find out what metadata is in there. And so for the whole project, it gives you a list of all the data elements that you annotated and their labels. These are the labels you chose during the annotation process. So this is kind of what data elements are in this data set that I could use to query for. It gives you the list of the subject IDs, right? Again, and at the top, it gives you metadata about the project, the name of the project, metadata that was in that data set description file. It also gives you information about the image types and the tasks that are available. And so, you get a lot of information for, little effort, let's say. Okay, so now what we can do is we could also look at more details. I think that's the next one. We can look at more details about the data elements with this /data element query. So if you just say /data elements, it will provide a data dictionary. Essentially, this is the information you put in during the annotation that ended up in the participants.json file, encoded in an NIDM file as well. And you can do some other queries, like you can ask it for specific fields. So you did that data elements query. Let me stop here. You did that data elements query, and you found out that there were some data elements in this file that you might be interested in. So now you've done a query where you've asked only for those fields, and it's given you, for all the participants, the value that they had for each of those fields. So this is the idea being, you can give it an output file, and you can export this data into R or SPSS or whatever. And the other thing that you can do right now is you can get details about a particular participant. So you could type in their subject unique identifier on the command line, or their subject ID for your study, because that's encoded in the NIDM file. Either of those will work, and it'll give you all the metadata that it knows about that particular participant. Okay. So if you were to learn Sparkle to query linked data documents, you can use PyNIDM query and give it a text file of your Sparkle query, and also do all kinds of custom queries. Then, essentially, this is what we're doing behind the scenes with PyNIDM. All those little REST queries and those parameterized queries in the back end, we're writing the Sparkle queries for those things. We're storing them, and we're having the query interface do those queries. So in this case, we're asking for how many T1 weighted scans are in this data set. We use the NIDM term had image contrast type and ask for values of NIDM T1 weighted. Essentially, that tells us we have 26 T1 weighted images in this data set. We can add a few more properties to that particular query that we want the path to the T1 weighted data set. That's the path locally. And we also want the location if there is one via DataLad. And so that will, again, return for you this query would return the subject ID, the ID used in the lab, the local path from that BIDS data set root directory, and the URL for Amazon S3. There's another tool that's similar to that BIDS MRI to NIDM tool that we saw that we annotate BIDS dataset with. CSV to NIDM will allow you to add assessment data to your BIDS dataset. So, to the NIDM file that describes your BIDS dataset. So a lot of times people will make their BIDS datasets with just the images, and then they'll have a bunch of CSV files or TSV files of assessments that are separate from your BIDS dataset. But when they do these NIDM queries, you really want to be able to query across as much rich information as possible. This tool allows you to add assessment information into your NIDM document, doing the same thing you did for the BIDS data set. Essentially, you run this, you give it a CSV or a TSV file where the variables are in the first row, and you go through that annotation process. And then what it'll do is it'll go into the NIDM file that you have from your BIDS data set, and it'll align, say, okay, do I have the particular participant ID that's in the CSV file in my NIDM file? If I do, I'll add the assessment data there. If I don't, I won't. There's some parameters to this tool that you can just tell it, hey, add the assessment data and the participant to this NIDM file, regardless if they're already in there. So there's different ways of running this. You could also run this without a NIDM file from the BIDS component, and this would produce for you a JSON sidecar file for your CSV file, just like it did for BIDS, but it won't be in a BIDS data set. And it'll produce an IDM file with just this assessment information, the subject IDs, but no project information here because obviously it doesn't have that. Okay, so other things you can do. Well, okay, so now we have the experiment data encoded in NIDM. That was done by annotating the BIDS data set. We have additional assessment information added to the NIDM file if you ran CSV to NIDM after and added some additional assessments. Now we want to add some brain volume information. So say we went off and we took these T1s and we went and did some Freesurfer segmentations of them. We have a tool for that allows you to take a Freesurfer segmentation. We also have some variants for FSL and ANTS, but let's focus on Freesurfer that allows you to take that Freesurfer segmentation. And if your NIDM experiment, your NIDM file that came out of BIDS MRI to NIDM has the same subject ID in it, it'll add the brain volume data into that NIDM file and link it to the original data. That's also in there. Of course, again, you can run this tool in different ways. You can tell it add the brain volume data, even if there isn't any experimental metadata there and so forth. So this, tool also has some different ways of running it. You can tell it, here's my subjects directory from Freesurfer, or you could also essentially give it a URL. So if you've stored the APARC ASEG files like on Amazon S3, but it doesn't really have the whole Freesurfer directory there, you can run this tool anyway and still parse that APARC ASEG file. You just have to give it some additional information. So essentially what it does is it iterates. If you're going to add this to an existing NIDM file, it iterates over that NIDM file. It says, hey, I found a subject, 26014, which is your participant that you're adding Freesurfer data for, and it adds it to the NIDM graph. It looks like kind of looks like one of the other assessments, like the participant.tsv file, the way it's encoded. except the predicates here have this weird Freesurfer number. And of course, just like your data element annotations for participants.tsv, there are data element annotations for the data elements from the Freesurfer export. Those can be either included in the NIDM file itself, or they don't have to be, because these Freesurfer data elements are common data elements. Now the data elements that you annotated for your data set were, personal data elements. They're things you used in your lab. These Freesurfer data elements, right, are they shouldn't change. These actually shouldn't change Freesurfer version to version. You may have additional data elements as the Freesurfer versions increase and they have new regions or new measurements that they're doing, but they won't change or renumber the old ones. So you don't have to include this kind of data element information directly in your NIDM file. All the PyNIDM tools will cache these sorts of common data element files for you. So you can still do your queries, you can still get out brain volume data, but yeah, with the tool, you have the option of storing these data element definitions directly in your NIDM file. If you had a bunch of NIDM files and they all had Freesurfer data, you wouldn't want to store this in each one because it's kind of redundant information. It makes the files bigger. But if you did want to have a completely, self-contained, semantically annotated, meaningful NIDM file, you can feel free to add these locally. And so then PyNIDM query has some other parameterized queries like data-DEBV, that's the data elements for brain volume data. It would return descriptions of the data elements that are specific for brain volume measurements. So anything that's done with the Freesurfer FSL or kind of ANTS annotation tool. You can also run another query that just says, give me the brain volume data, and it will, for each ID, give you all the data that it's collected from the Freesurfer output. So what are we doing with all these NIDM files? So we've gone and annotated, ReproNIM's gone and annotated some of the publicly available data, Abide at HE200, this core data set. We've also done or are still working on, but have done mostly the OpenNeuro data sets. We made a little GitHub repo where we're making these NIDM files available if people want to use them. They also have some brain volume data used for the Simple2 project in ReproNIM. And essentially, this is how we did it. We did, BIDS, MRI to NIDM first on the BIDS directory. We added phenotype information. So in the case of, I think it's Abide, there is no participants.tsv file in the BIDS data set. There is a separate phenotype CSV file that's separate from the BIDS data sets, but I think it covers all of the sites. So how do we do that with our tools to get an IDM file? We did BIDS to MRI to NIDM. We had no annotations to do because there wasn't a TSV file there. Then we did CSV to NIDM. We gave it that phenotype file and we told it to add to the NIDM files, and it would go through, and every time it finds matching subject ID, it will add that phenotype information in. Then we ran Freesurfer, ANTS, and FSL to compute brain volume data, and we use those tools to add that information to the NIDM files, and then we can do complex queries. There seems to be a missing slide. I apologize. So then these NIDM files are being loaded into a ReproNIM tool called the Repro Lake. The idea is it's a metadata search engine. Currently doesn't have a easy to use interface. We're working on that right now. You can just log in and do Sparkle queries, but essentially it has NIDM files from all these studies you see here in the OpenNeuro data sets. And so we're getting, and by using that Isabelle concept level query mechanism, we're getting to the place where we can, build a nice metadata search engine across publicly available neuroimaging data sets where you can identify subsets, cohorts that are of interest to you. And in this case, since they're all publicly available, you could just go out and get them. In the case where some data sets require, IRB approval or something like that, you would get information about the cohort from that resource, but then you would be directed to that resource to provide them with your IRB approval or whatever they, sign their research agreement or whatnot. So that's still work in progress. The Repro Lake is there. It's a graph-based database. It holds these NIDM files. Just the interface on the front end isn't ready yet for sort of prime time, unless you can write Sparkle queries, and then it's there for you. So what other PyNIDM tools do you have available? You can convert from the turtle format to this JSON LD or some of the other syntaxes. These are all kind of works in progress. And I think they all work, but as new versions of packages come out, sometimes they break. But right now, it seems like everything is pretty stable. You can concatenate NIDM files together. That's just a simple concatenation. So if you wanted to take 20 of them, make one NIDM file, you could, and then store that somewhere in your archive. You can merge them. So you can merge multiple NIDM files together. This is something you should be careful with, though, because you can merge on subject ID. And so you should really know that NIDM file 1 and NIDM file 2, the subject ID, number 50 is in fact the same participant, because it's going to merge them by assuming it's the same participant. But this is useful if you had, NIDM files with just brain volume, like Freesurfer data in it for each subject. And then you had an NIDM experiment, experiment metadata file from your BIDS directory structure. And then you had another NIDM file with assessment data. You can kind of merge it all together on subject ID. And PyNIDM Visualize lets you see the graph in gory detail and makes a little PDF with metadata and stuff. If you care to see how big these graphs actually are, you could use Visualize for that. And the last tool that's very much a work in progress, and it hasn't been merged with the main repo, but I'm pretty excited about it. It's almost ready to go, is this nice little linear modeling tool. You basically can give it, again, a list of NIDM files. You now know how to use PyNIDM query to figure out what data elements are in these NIDM files. And then you can use those data element labels and create yourself a nice little linear model using sort of typical R style expressions. And you can look at, relationships, just simple relationships between some independent variables and dependent variable. You can do some contrasts with, and you can, I think right now it supports L1 and L2 regularized regressions as well. So you can choose to do a regularization, and it'll kind of do some cross-validation to figure out the regularization weight, and gives you this nice little output. And the idea here is, okay, so I've gone out, I've queried across a bunch of data sets. I've identified like some cohort that I might be interested in. I've now downloaded the NIDM files. I'm going to do some simple, just linear models, high level things, just to kind of see, does it look like this is worth pursuing or not? My research questions. And if so, then maybe I'll go off and do something far more sophisticated, or maybe this is all you really cared to know. Maybe there's this simple relationship between, in this case, I think, I don't remember what Freesurfer 3257 is. I think it's like the total brain volume or something. It's total brain volume. Let's just say it is related to sex, age, and group. And is there an interaction between sex and age and brain volume, that kind of thing. And there was a lot of people worked on this, so I'd like to thank everybody. And it's been started as a grassroots effort a long time ago, and I think it's coming along quite nicely. And we're starting to get some tooling around the linked data files to make them more accessible and more usable by folks. Thank you. That's it.
Thanks, Dave. That's quite the collection of pictures you had there.
Oh yeah. No, these are good. I mine the internet to find. Do you remember the?
So if there are any questions from the audience, again, it's so much content, and the good news is these will be archived and encouraged to install your own little PyNIDM and go back through this video and do it hands-on in your spare time.
Well, yeah, I mean, I think the right way of thinking about this is, I got a BIDS data set, let me create a data dictionary for it so that my BIDS data set is more usable to the next postdoc, graduate student, whomever comes in the lab in 2 to 3 years, 5 years. At least I can hand them a BIDS data set with a JSON sidecar file in it, a data dictionary. And they're going to be able to make sense of that BIDS data set. I think that's the way to start looking at this. And then, once you move beyond that, you can start to look at the NIDM files and think, wow, what can I do with this? What additional things can I do with this? How can I integrate it into my Python tool and, make better use of BIDS data I think that's the place to start. And then when you think about making your data set public, that's when, oh, these NIDM files would be great. Send them to Repro Lake, or I suppose when you want to share them out, send them to Repro Lake. And yeah, hopefully we'll someday have a linked web of neuroimaging data. We'll see.
BJ writes in there, thanks, and they're getting several requests for the recordings and the slides. Okay, that will certainly happen. The other thing I wanted to remind one of is some of these things you only have to do once. If you always collect your, behavioral data in certain ways, or always collect your stuff in the same way, well, if you have an annotation for that file, the way you collect it, well, you have to decode it once for this, but then you can always reuse that in other situations. And as the set of these annotations get built up, this concept of repro schema is a place where these things can be shared. So if anyone's doing the same assessments, well, you can create these in a way that already knows this information and make that, streamline that in the future. I don't know if I want to say a little bit about that.
Yeah, I was going to show, so I didn't show the parameters for BIDS MRI to NIDM or CSV to NIDM, but there's a parameter to BIDS MRI to NIDM. Essentially, it says JSON map, and that is if you supplied the JSON sidecar file from a previous annotation to the tool, it would use that for the current, participants.tsv file. And if it finds an entry in there that matches one of your variable names, then it won't even ask you for an annotation. It'll just use that. So you can essentially run this tool, like Dave said, if you have a data dictionary already done and you're doing the same, using the same variables coded the same way, you can just provide that previous one and it'll create your NIDM file without asking you any information at all. It'll also store that JSON sidecar file into your BIDS directory as well. That, the new BIDS data set that you're trying to annotate. Sorry,
and I'm mindful of our time, so folks may have to start running off to their next things, but thank you so much, Dave, and we will archive this and make it available, and everyone knows how to get a hold of you and the whole ReproNIM team to keep this train rolling, and as much support as we can to all of our newfound inoculated folks with the repro technologies.